Okay, now we are going to see some quantum systems that we can use to make qubits. All right, many types of quantum systems can be used to make qubits. One example would be, suppose I have an interferometer. Okay, a two beam a two beam interferometer. What is this? Well, this is basically a device. All right, a device like this, that has two channels. Suppose that has two channels or two beams for light to pass through it. Okay, that has two channels for light to pass through it. Light can pass through this channel or it can pass through this channel. Okay, so if the light I mean photons can pass through either the upper channel or lower channel. So if I send one photon, it can be in the upper channel or it can be in the lower channel. So if the photon is in the upper channel, we say that the state of the photon is 1, 0. If it is in the upper channel, upper beam, and if the photon is in the lower beam, we say that the state of the photon is 0, 1. Well, simple enough. All right, so but the postulate of quantum mechanics tells us that the state of a quantum system can be any unit vector of that corresponding Hilbert space. So we can also have a state of the photon that is like this. Suppose 1 over root 2 and 1 over root 2. So what does this represent? Well, we can break this system down into the upper and lower beam channels. We can write this as 1 by root 2 times 1, 0 and 1 by root 2 times 0, 1. Okay, so what does this mean? This state represents that the photon is in the upper beam, and this state represents that the photon is in the lower beam. So you see that there is some kind of a mixture of the upper state and the lower state. Well, classically we might want to think that the photon has been split up and it is, well, some part of the photon is in the upper beam and some part of the photon is in the lower beam. But quantum mechanically, well, photons cannot be split up. You see, the photons are the fundamental units of light, so you cannot actually split them up. There is only one photon. All right, so the state of the photon, we call this state the wave function. The wave function corresponding to the photon is at the same time in the upper beam. Part of the wave function is in the upper beam and part of the wave function is in the lower beam. Okay, the photon, where is the photon? Well, this is actually one of the main conundrums of quantum mechanics, that quantum mechanics doesn't answer that where the photon is in this type of a situation. We will see that when we try, what happens, what if we try to see, if we open up the device and try to see in which beam the photon is, what happens. All right, so for the time being, we will just accept that photons can be in states like this, where the wave function or the state corresponding to the photon can be, although there is only one photon, the photon cannot split up, the wave function of the photon can be at the upper beam and in the upper beam and in the lower beam at the same time. All right, these type of states, they have a special name. They are called superposition states. right? They are called superposition states. Well, the name is kind of intuitive. You see that the photon is kind of in a superposition of the upper beam state and the lower beam state. Although there is only one photon, I am repeatedly saying this because the photon doesn't actually split up. It is the state of the photon or the wave function representing the photon that actually that partly resides in the upper beam and the lower beam. Alright, so a 2-beam interferometer can be used to make a qubit. Alright, what else can we use to make a qubit? Well, we can use atoms. Okay, we can use atoms. In particular, we can use two-level atoms. What does that mean? That means, well, suppose I have an atom that has, well, that basically means I have an atom that has two energy states. One I can call the ground state. One I can call the ground state. Call this the ground state, and this the excited state. All right. Okay. So if the atom can be either in one of these two states, if I have a two-level atom, a two-energy state atom, then atom, suppose this is represented as the state G, ground state. G represents for ground state, and this E represents for excited state. So if I have an atom that is in the state E, then, well, I can say that okay, it is in the excited state, or if it is in the state G, then it is in the ground state. But we can also have an atom that exists in a superposition of these states. All right, we can have states like this, E plus 1 by root 2G. Okay, again, like the previous example, that does not mean that the energy of this atom is between these two states. Suppose this is 1 electron volt and this energy is 2 electron volt. This state does not mean that the energy of this atom is 1.5 electron volt. No, this does not mean that. In fact, like before, if we open up our atom, if we want to measure the energy of our atom, we always see that either the atom has an energy of 2 electron volt or it has an energy of 1 electron volt. We never see that the atoms have energies of 1.5 electron volts. Well, these numbers are definitely examples, not actual energy levels, but we never see energy levels, energy values between the two states. All right, we always see either one energy value or the other energy value. So what does this state mean? What does this mean? This means that the wave function corresponding to the atom is split between two energy levels. That does not mean that the atom has an energy between two energy levels. It means that the wave function of the atom or the state of the atom is split between two states. Okay, all right. So using this we can make qubits, and you can guess that we can use many other types of two-dimensional quantum systems.